the plan is that I think I probably moved too fast last time, so we didn't actually go through examples on single-stage amplifier analysis. So I would like to briefly go through 2 examples as to what kind of questions you might be faced in terms of design problems or calculation problems. How does one approach when you actually face with a particular circuit? So we actually last time we only have time to go through 1 example. Today, so I would like to probably go through some design examples as to what are the approaches or directions as to how one approach a problem. So we're going to go through 2 examples, and then one on common gate stage, and the other is on common drain structures. This is mostly to address, this is especially to address a body effect. So we didn't actually address the effect of, I think I talked about body effect a little bit. I'm just going to explain how that affects particular circuits in terms of its analysis. Why do you need to take care of that? Or consider body effect, the effect on circuit analysis. So then we're going to move on to chapter 9. As I said, we're going to talk about there's actually in chapter 9, let me outline a little bit. So in chapter 9, we're going to talk about one of the key structure, which is called the cascode structure, and then the other is called the current mirror. So let me outline what is next so that you get a sense as to where we're at and what we're going to do in the following semester. So in I think chapter 10, this is the future. So what are the key topics we're going to talk about? On chapter 10, I'm going to spend a lot of time on one of the key topics called the differential. So one of the key concepts is the concept of having differential circuits rather than single-ended circuits. So we're going to compare the concepts. We're going to spend a lot of time talking about differential. And differential pair is one of the simplest structures in constructing differential amplifier. We're going to talk about that. And lastly, on chapter, I believe, 11, we're going to talk about frequency response. This is a very big topic. So these are the things that is coming in the future. So you get a sense as to where we stand. We have the basic building block of single-stage amplifier. How does you combine them and to construct certain structure which is useful in terms of larger circuits? And then you address different issues. One is to talk about this. This is to increase analysis on speed, because we didn't spend much time talking about speed of the circuit or bandwidth. So this is just to expand direction as to which are the key components in addressing or analyze a circuit. And this is one of the structure which allow us to minimize noise. So we're going to talk about that. So this is what we're going to cover until the end of the semester. So you sort of know where we stand. So it's probably at the middle of the midterm, after midterm. So we're probably at the middle after having all the single-stage amplified analyzed or introduced. So next we're going to go into more complicated issues and structures dealing with these type of issues. So as I said, this is to address noise. Okay, one is to address noise, the other is to talk about speed. So let's come back to single-stage amplifier, a common gate stage. So let's say I give you a common gate amplifier, looks something like this. So there's, as I said, there's 2 types of problems. One is that I give you all the parameters, you calculate what happened to the circuit. That's a basic, straightforward circuit analysis problem. So circuit is given with all the parameters given, and you calculate what happened to the circuit, finding out its input-output resistance, finding out its overall gain, and its biasing condition, that sort of things. The other type of question is called a design problem, meaning that I give you a structure, and you determine the parameter in order to fit the specs being set. So we're going to go through an exam problem as to how one approach this type of issues. So in the future, you'll probably mostly be faced with design problems. And then you go back and do analysis to make sure that whether that fits your first order assumptions. So let me just give, this is with a bias. And so it's biased with a resistive network just to make our life easier. And the input terminal is coupled, so input is coming in here. And this is my output terminal. So you take common, based on this, if I give you the circuit, you're looking at where the signal coming in, where the signal goes out. You know that it's a common gate structure. The gate is being biased by this resistive network, and input coming in from the gate, output going out at the drain. So knowing where your input output are, you should be able to define which operation, which type of architecture you're actually using. So this is a common gate stage. We want R1 is set to 500. And the target, let me give device parameters, M1. So for this transistor, we know that the technology parameter give us 100 microamp volt square, and it has a threshold of about 0.5 volt. Okay? And then your spec tell us VDD is 1.8 volt. It's typically being defined by technology. The voltage can be, or supply voltage is a system provide level, so 1.8 volt. And then I have two specs, which is the power budget. Power budget meaning that the maximum power can be dissipated by the circuit. Let me misspell it, but. So the power budget is set to 2 milliwatt. And then I need to design to meet a certain spec. And most, as I said, in most of the common gate stage is used for taking in current signal or impedance matching. So let's say if this is for impedance matching, meaning that I'm setting my Rn to 50 ohm. This is to say that this is defined for impedance matchings. So typically, when your input is connected to an antenna is 50 ohm, you want it to be balanced so that you get the maximum power coming into the system. That's called impedance matching. So basically, I want this to match whatever my antenna resistance is. So that's the spec for this circuit. So let's move on to what you need to determine. So basically, you need to know what your biasing conditions. So you need to determine RG1, RG2 for setting this biasing condition, right? In order to meet this criteria. The other thing we need to know is that you need to design. I already know R1, so the next thing is that I need to design M1 so that W over L, the size of transistor. So there's 3 unknowns are needed. You're setting, this is R1, RG1, RG2 is the parameters you use to set up BG, and device size is how you set up GM. So let's do some, so first of all, for power budget, allow us to determine what is the maximum current that's being flowing through the system. So let's say for power, so you start with power, typically you start with your boundary. Use yellow. So let's start analysis. So typically you start with your boundary, your power dissipation is your limit, is 2 milliwatt. So I know that the maximum power is available, total power available is 2 milliwatt, 1.8 volt. So that's 1.11 milliamp. So you have two branches of current. One is IDQ. The other is the biasing current, let me say I1. So this is the total amount available. So this should be your IDQ plus I1. The total current should be smaller than your biasing current in I1. So you can separate between the two. You make a decision. So typically what we want is that you want to keep your main current. This is just biasing, especially when gate current does not taking any, gate does not taking any current. Therefore, you don't actually need too much current for biasing. Therefore, you want to keep it as small as possible. So I make a decision so that I set. This is arbitrary, so you can do your own design. This is just a design solution. One of the design solutions, as long as it does not exceed the boundary. So I'm using more than 90% of the current for biasing. Let me set my IDQ to 1.1 milliamp. Therefore, my biasing current will be left to only 10 microamp. That means that I would need large resistors to set this up, but that's fine. Depending on your design, your boundary in terms of determine how do you get this resistance. So there might be some trade-offs, but this is just one of the settings that allow us to go in to further design this. And then because this is the case, I know the voltage at this particular biasing point, which is VR1. So therefore, VR1 will be IDQ times my resistor R1, which is 500 ohm. Therefore, it gives me 550 millivolt. Okay, so I already know the current. The other thing is that I need to determine, so now once these are defined, the next thing is to determine W over L. Before determining W over L, you should know that, how does one determine W over L? You start with your requirement on GM. So we know Rin, I should say. Because Rin, in this case, if you're looking in from here, is 1 over GM in parallel R1, right? So we assume that this, you can actually include R1 or without, but it's approximately, so this will give you, will still be approximately 50, very close to 50, because it would maybe 10% difference. You can make it more accurate. I'm just assuming that this will be much, much larger. This will be the dominant resistance. Therefore, we know that GM, there's various ways of expressing GM. In this case, I know my current, and let's say, okay, so once I know this, I could use different expression of it, determine whether my W over L is, or you could determine your size. So the way to do this is that you want to set your biasing conditions. So we're going to set a VOV, a overdrive. You can set your own overdrive depending on what is the biasing condition. We already know that this is 0.55. So you should design where your VG should be, determined by the overall scope of your biasing condition. I know that my overall voltage is 1.8 volts, so somewhere in the middle would be good. So I'm setting my overdrive to about 0.1. That's 11 millivolt. So let's say I'm setting an overdrive, then this will give me, let me rewrite this. Because GM is, you can set it up with 2ID VGS minus VTH. We know that GM can be expressed this way when, this equation is used when W over L is unknown. Because we don't know what WL is yet. But we know the current and we know the GM. Therefore, this is known. We already set it up to 1.1 milliamp. This is set by requirement of Rn. This is 1 over 50 ohm. So you insert the number, you get a definitive overdrive. This is the overdrive. This is VOV. So we know that VGS minus VTH, by these two numbers, we should be able to get your overdrive as to 110. So let me make sure I got it. 0.11 volt. So you get this simply by setting up my current. And GM, when this current is fixed, GM is fixed, your overdrive is fixed. So once this is fixed, then you can go back to determine. Remember, what we need to know is the W over L of this device. So you go back to the current equation. IDQ equals to 1/2 mu n Cox W over L VGS minus VTH. I'm just going to use the first order equation in saturation. So this is known. This is 0.1 milliamp per volt. This is 0.11 volt. And this is 1.1 milliamp. So it will give you one answer of W over L. Right? This is known, so we can get W over L. The ratio is 200 over 0.11. So it's a fairly large transistor, wide transistor, I should say. And this is typically not a good number because just by, I didn't actually define, but based on the VDD, it's supposed to be a 0.18 micron technology, meaning that your lens probably is the smallest lens you can draw is 0.18. So you want to make sure that, let's say if this is 0.18 micron technology, this is just based on VDD at 1.8. Suggests that your gate length should be larger than, so that is to say this is something that will violate design rule because it cannot be made. Therefore, you could actually shift it to 400. So a better answer will be this. So this would then be larger than your minimum length. Okay? And finally, remember what we want. We already answered this. So I already know that W over L equals to 400.22. So I determined the size of my transistor. The next thing is to determine RG1 or RG2. So this is fairly easy. This is just a DC biasing part. So then VG, your gate voltage will be VR1 plus VGS. So VR1, this will be V threshold plus a overdrive. I know that my VR1 is 0.55, or if you want to use millivolt, that's fine. And this is 0.5 volt, and this is 0.11. Therefore, I should know that the targeted gate voltage should be 1.16. Did I get it right? Let me fix my mic again. Good? So I'm just summing up all the biasing voltages. This is VGS. So it's overdrive plus a threshold, right? You put it over. VGS is, let me write it down. This case, VGS equals to threshold plus the overdrive, VOV. Okay? Yes? I total 是这个两个相加。是从这边来。假設你要這樣接的話，就是這個 I total。Yes, yes. Supposed to be 就這兩個相加了。你可以想象它就可以接在一起啊。It's the same terminal if you shift it. 整個電路對，整個電路。Power dissipation 你就要考慮你消耗在 bias 跟消耗在你自己本身上面。This is total the dissipation of this single circuit. Okay? Good? Okay, so the next thing we're going to talk about, so then you determine RG1, RG2. But first of all, we know that therefore RG1, RG2, there's a ratio. The ratio between the two should be 1 point, I should say, RG1. The ratio between two should be 1.16 over 1.8. So we know that for this voltage divider, let me see, RG2. Okay, so we know that it has to fulfill this ratio in terms of voltage dividing. And the other thing is that then the absolute value of this resistor is RG1 plus RG2 should equals to I1 times, VDD divided by I1. So the total current, total resistor, the sum of the resistors should equals to 180 k ohm in order to fit I1. In order to set I1 to 10 microamp. If you set I1 to 10 microamp, this is what you get. And then we could find out the absolute value. Therefore, RG1 is 64 k, and RG2 is, you can do the exercise on your own. Did I get it right? Maybe. 180, right? Okay? So this is just as I said, it's a design problem. Your answer might not be the same as mine, but the only thing you need to do is to make sure that it fits its spec. So we go back and check. It can be a good or bad design. There's following judgments on that. But you set up to make sure that it especially fit the spec. One is input resistance. The other is power budget. Okay? Questions? Good? Okay. So I'm going to quickly go through another example on common drain circuit. So let me give you an example. So let's say if I have a source follower that's common drain. I need to determine its biasing current in order to determine its output resistance. So let's say the circuit looks something like this, VDD. And then I could actually bias this circuit this way. I'm using sort of like a self-biasing scheme to set the biasing voltage. Okay? So this is M1. And input coming in here, and output going out at the source terminal. Let's say I want to set okay. So the design problem is, we're going to consider two cases. One is that you include body fat, the other is exclude body fat. And we're going to see how much discrepancy there is in your design solution. So let's say I'm just going to set it up first. So this is 1 k ohm. And this can be an arbitrary number. This does not really change too much, only in terms of speed. So you don't actually care. There's no DC current flow. Okay, and this is 1.8. Let me see what are the parameters. So we're going to give you threshold. Okay, once again, mu and Cox. I'm going to use the same mu and Cox, which is 100 microamp rho square. And it's VTH 0, meaning that at zero bias, zero body bias. Okay, it's 0.4. So first of all, let's ignore body fat. I'm going to introduce the body fat coefficient when we include it. So the key is that if you ignore body fat, we can actually find out what is the corresponding GM to find the transconductance, because this would then determine your output resistance. Remember, if you're looking in from here, RL will be RS in parallel GM. Therefore, GM will determine the characteristic of this source follower, the key performance factor of the source follower circuit. So let me use the yellow. So when you ignore body fat, first of all, we need to find out what is its, oh, sorry. And also, we already know that it's set so that the current is at ID1. ID1 is set to, the current is already set to 1 milliamp. Therefore, this is the case, then I know the overdrive, I should say VL, at DC level it should be 1 milliamp times RS, which will give me 1 volt. And the overdrive of the circuit, I should actually set it up. The overdrive of the circuit is VOV, is VGS minus threshold, which is, what is your gate voltage? Anyone knows? What is the gate voltage at steady state? VG. What is it? No one knows. DC, this is open. Is there current on the resistor? No, therefore this voltage is 1.8 VDD. Minus minus source voltage. I know that output is my source voltage, so this is Vs minus threshold. This is actually VL. I should just write it down. Yeah. So it's VDD minus VL minus VTH is your overdrive. So I know my overdrive is 0.3 volt. So I could actually get my GM, transconductance GM, without knowing the device size, because this is the design. I already know the current. So whatever W over L will give this current under the circuit. So this will be 2ID. As I said, without knowing W over L, you should be able to use this equation to get your transconductance, which is 66 milliamp per volt. Okay? So this is fairly large transconductance. Okay? That's good. So the next thing is that this is because we ignore body effect, meaning that we assume the threshold voltage does not shift because of this high source voltage. But what if we include that? So as I said, to include body effect, we need to know how does one calculate the shift in threshold. So let's give the equation. The equation is the actual threshold will actually increase because I will expect my threshold to increase because this voltage, VSB, is no longer 0. You have a raise of threshold. So gamma, let me review the equation. So VSB plus 2 phi f minus 2 phi f. So that's my body effect equation. And we need two parameters, which is gamma is 0.6 volt and a half, and then 2 phi f. This is typically 0.8 in most cases. Okay? Yes. Yes, yes. 因为我们 ignore body effect. Sorry, this is, let me just highlight it. This is BTHO. Did I make a mistake? 减4应该是0.4吧 Sorry. Yeah, it's 0.4. So for this number, that may be wrong as well. So this will be 2. Let me readjust this. So this will be 2 milliamp divided by 0.4. And that will be 5 milliamp per volt. Right, you're correct. I'm coming. Why do I get a point? For some reason. Yeah, made a mistake. Good. Okay? Yeah, it's actually much simpler number. So this will then suggest that this is actually easy. This will then suggest that you have a, let me get it right, inverse of that. Correct. This will then suggest that your 1 over GM is 200 ohm. Right? So that's your output resistance at the level 200 ohm. In parallel with this, and then will be somewhere a little bit higher than 200. Okay? So let's look at, well, once you include, what is the impact on its overdrive, mainly on overdrive. So what we want to do is to find out the threshold, the actual threshold when VSB is no longer 0. So we know that source to body, sorry, I didn't highlight, body is here. Body is by default connected to ground. This is body. So I know that body is ground, source is at 1 volt by this setting. That is to say, VSB equals to VSB equals to VSB equals to 1 volt. So you simply insert that in. This will be 0.4 plus 0.6 square root 1.8 minus 0.8. And then we get the threshold slightly higher. Okay? What is the implication of this is that you would then have a much okay? So then in this case, you will actually have the implication will be to sustain the same amount of current. It means that you would then need a much larger W over L. From this, we can actually go back and calculate its W over L. But in this case, what happened is that your overdrive will then be, as we did, your overdrive will be 0.8 minus 0.67. Therefore, we'll have a much lower overdrive. I should say 1.3, correct? So based on this circuit, you would then have a much smaller 1 over GM because overdrive is at the bottom. So 1 over GM will be higher. At the cost, I should say GM will increase at the cost of increased WL. The reason why we don't see this is that we didn't go back to check under this balancing point, under this 1 milliamp. If I'm considering body fat, you would then need a much larger W over L. The reason is because of this equation. Let's say this remains the same, but your overdrive becomes smaller, therefore your W over L needs to be higher to sustain this same amount of current. So even though we get, you see that including body fat, to keep this, meeting this standard, you would then need a much larger transistors in order to meet the same results. So if you go back to check W over L, including body fat would then request a much higher, much wider transistors. Okay? So that's the main difference. When you include it, meaning that your overdrive will be less, causing you to increase your W over L in order to make sure that the current level is the same. Okay? Good? So you can do the exercise to find out for this two design, to meet the same requirement, include or does not include, what is the request on W over L? VSB, because the source voltage is VL. Vs equals to VL is 1 volt. Body is ground. Body always ground by default. If you do something, you can actually have something called a source body tied structure, but that's a costly solution. And then there will be complications if you connect source and body. By default, and then, I want to mention one thing just to give you an overview. In most of the integrated circuit, remember we said that for transistors, your body, especially if we already introduced the sort of twin well example. I don't know if you remember. We have a little bit of time. If you look at a CMOS technology, this is called a twin well, just to do some twin well process. You start with a P substrate. And then you have N plus, gate, right? And P plus, gate. So this, from the left, is the N channel, right is the P channel. And what happened is that you would then have N wells. And these are P well. But because P well is connected to P sub, therefore you only have one substrate. So all of them are connected together. So that's your to ground. So that's your body. Body is connected through here to here. You can actually do implant within well, but it's still the same. So if you're doing twin well process, this is called the twin well process. For N-channel device, there's only one solution. Your bodies, all the bodies, multiple transistors, like billions of transistors, all the bodies are common to ground, or maybe whatever minus voltage. Because you only have one choice. Everybody is grounded. Everybody's body is grounded. Even though I have this well, but this well is the same potential as substrate potential, therefore they have to share the same node. Everybody share. But for PMOS, I can actually build wells if you need to. So the main difference is that for PMOS, the contact is substrate contact, it's body contact for PMOS. Even though I'm only having twin well process, this is N+. So this can be individually made, meaning that if I'm making another PMOS here, I could create another N well, and P+, P+. Okay, so this VB1, let's say this is VB1, 2, and 3. So VB1 can only be 1. There's only 1 because they're common to substrate. But N well is not common to substrate. Therefore, VB1, VB2 can be individually therefore, this well can have a different potential from this well. So if that's the case, then you could do what we call the source body type. We'll then have independence of my biasing condition because this well and this well are not connected together. So there's a main difference if you're doing twin well process. Of course, there's like triple well to surround it so that you can have independence. But anytime, so just to give you a sense, if you're having a twin well process, this simply implies that your N-channel transistor will not, your transistor, the body of your transistor is not within your control because it's shared by everybody. But the P well, if you're doing PMOS, so this is to say that if I'm doing PMOS transistors, I then have the choice of individually biasing this body. This is VB3. I have 2 transistors in different well, then this will be VB3. I will then have the flexibility of individually biasing them. Okay? So if I want to avoid body fat, one of the things can be done is to do this. I could short source and body so that VSB equals to 0. I could short them so that it will always be 0, and there will be no body fat. But this comes with the price. You need individual wells. So this 2 transistor needs to be in different well. So it takes a lot more space, if that's the case. Okay? Any questions on the previous discussions? 我稍微简单讲一下，就是body fat 最主要的影响就是它会降低你的 overdrive， 因为我们的 threshold 会把，你看我们本来是 0.4， 它会降了差不多1/3哦，所以你的 overdrive 降低的情况下呢，代价就是要有一个比较大的 transistor。等一下会去看，你可以回去推这个 transistor， 就你在假設你要 design 達到不考慮 body fat 的時候，算出來的 transistor size 這個需要大很多，就表示你要有更多的空間去讓這個電流流，因為你 overdrive 不夠。去 sustain 這個電流，所以這個主要是 body fat 的效應哦。那通常啦，因為 body fat 很討厭，就是說它會 吃掉你的工作空間哦。大部分情況針對 source follower 主要是這樣子。所以呢，如果你要避免它的話呢，就是你可以就是故意把 source 跟 body 接在一起。那這個是必須要建立在這個 body 的 potential 是獨立的，就是它是跟別人沒有共用。如果它有跟別人共用的話，那你就沒有那個空間。所以我剛剛講，如果你是用我們叫做 Twin-Wall process 的話，你的 body by default 就是大家一起共用。那只有 PMOS 不是共用，所以 PMOS 你有這個空間，你可以畫大一點，你可以把兩個分開。或者說你可以一人一室啦，就是 PMOS 上你就可能比較有這種一人一室的空間，可是 N 就沒有，大家就是共用洗手間這樣子，你懂我意思？所以這個意思就是說我有這個空間，我一人一室，我們兩個這個的 bias 是獨立的，可是這個就不行，所以這個的話就是大家共用洗手間的概念。OK， 你的那個 body contact 就是共用。那所以獨立有獨立的好處，独立的好處就是我可以獨立去決定我的 body bias， 我要把它設在哪裡就設在哪裡，這樣的話就可以避免 body effect 這樣子。OK， 好 ，Let's take a break for 10. We come back and then we're gonna venture into chapter 9 and talk about cascade structure. Very interesting. Okay, so we're gonna enter into chapter 9. Which we're going to introduce this. We're going to talk about two topics mainly. One is the cascade structure, the other is current mirror. So for today, we're probably just going to start on introducing what is a cascade structure and what is the purpose of having a cascade structure. So typically, when we use a cascade structure, you mainly wanted to substitute something. You wanted to have a more ideal current source. You want to deliver a more ideal current source. More ideal current source meaning that, typically meaning that it has a flatter input output resistance. What is an ideal current source? If you look at its current and voltage relationship, ideally you want it to be flat. So this is an ideal current source characteristic. If you use an ideal current source, it should be flat, meaning that the output resistance should be infinite. That's what an ideal current source is. But we know that if you're using a transistor, for example, bipolar transistor or MOSFET, because of early effect, what happened is that if I'm using a single transistor, it will look something more like this. So if I'm using a transistor, it will look something. This is like a single transistor. You use a transistor to simulate its current voltage relationship. It will look something like this. The slope will be RO. So what we want is that we want to make sure that if I'm not satisfied with this output resistance, what can be done is that how do I make this slope coming down? So you want this slope to be somewhat here. So this is what we want in a cascade structure. So in a cascade structure, you would then push down the effect, increase the output resistance mostly, simply by this feedback loop we talked about when you're using a common gate structure in between resistors. So you get something more like this. Okay, so that's basically what we want to do. The other thing is that you can do an amplifier. So the cascade structure topology, mainly the first thing you see that is that it will then effectively increase. So it has one of the main feature of a cascade structure is that it effectively increase output resistance. So this can also be beneficial for amplifier circuit. If you think about an amplifier, typically we use a voltage control voltage source. But if you use something called, I think most of the transistor amplifier, it's more similar to a transconductance model. Let's use a transconductance model. We call it transconductance two-pole model. If I try to explore my circuit into any amplifier using a transconductance two-pole model, typically we use voltage amplifier two-pole model. You can use transconductance two-pole model. It will look something more like this. It will be a Norton equivalent on the right. Rather than having a voltage source. So this is called a transconductance two-pole model. It will then include 3 key parameters. Also, input-output resistance. And instead of having a open circuit voltage, it will be GMS. Okay? So a transconductance two-pole model consists of a transconductance instead of a open circuit voltage. So GMS is defined as IO versus Vn. So let's say if this is my output current when VL. S stands for short, when it's short, IO when it's short. When this is short, you see the whole overall current. Okay? Let me just be specific, VL. And this terminal, the voltage across is VL. So if you look at a transconductance two-pole model, what it means is that your voltage gain, if in this case, my voltage gain, if I go back to look at voltage gain, it will be GMS times R out. So for the amplifier application, GM is the way, remember the sensitivity when you modulate the current. So this is typically determined by transistor design, W over L, biasing current. And if I can boost this, it simply means that my overall gain can be boosted. So as an amplifier, gain can be increased by RL. If my transconductance are the same. So if I keep the same transconductance, if I can boost my output resistance to a high level, I can also get a high gain single stage amplifier. So that's the reason why we want to introduce cascade structure to boost. By the boosting of effective resistance, I could actually increase my overall voltage gain. Okay? So let's look at its structure. So as I said, the main reason is to deliver high output resistance. So let's look at a cascade current source. So let me just write it down. So I'm going to just write down a cascade. So if you want to deliver a cascade current source, depending on whether it's for loading or I should say for pulling up or down. I mean by this is that if I'm using this current source as a pull-up, meaning that it's connected to VDD, so pull-up is to VDD, to high voltage. Pull-down is to ground. Let's just say my lowest voltage is ground. Okay, so you could actually have, if I want to deliver, for example, current source like this, let's say for source follower circuit, that's a pull down. Pull down loading, you put it in the bottom, or sinking loading. If I'm doing circuit like this, a common source amplifier, so this type of current source is called a I2 is called a pull-up, I1 is called a pull-down. Okay, just to give you an example. Okay, so how does one realize this? And let's just write a pull-down example. So for pull-down, a cascade structure will look something like this. I would then have two transistors stacked together with a fixed bias. Let me have it, VB1, VB2. This will be similar to a I1. Okay? I'm just drawing the BJT. You can do the MOSFET version as well. For I2, I2 pull-up will be something more like this. You're going to use PMP instead. So this will be Q1, Q2. Okay? Q4, Q3. I don't know. Did I label it correctly? So typically you want to have 1, 2, 3, 4. There's a lot more transistors. So this will be equivalent to a pull-up current source, I2. So this determine, depending on whether you want to pull it up or pull it down, you use MPN or PMP. So we can also draw the MOSFET counterpart. Let me just draw it over here. So if you want to do the MOSFET, this will be N channel, 2 N channel to ground, M1, M2. Okay, for PMOS, for pull-up, you use PMOS. And to do a current source, you typically want the bias of your gate to be fixed. So this simply means that it's a DC bias. All the gates are DC bias. Okay? So as I said, this type of cascading structure is to enable the increase of output resistance. So let's look at how does your output resistance changes. So one of the key is that the key performance factor is this. You want to press it down. You want to make sure that the slope actually decreases. So the key performance factor is actually R out here. Right? You want to find out what the RL is for these two cases. So let's look at a MOSFET version first because it's easier. So for a cascade, I should say for a MOS cascade current source, it looks something like this, right? You have two transistors. The labeling will depending on what kind of fashion you want from the bottom to the top. So you start with M1, M2. M1 is the most bottom one. M2 is on top. And then you bias this. Let me just follow my convention from bottom to top. So what I want to do is that I want to figure out what is its output resistance. Looking down from drain. So remember our discussion on common gate structure. This will be very similar to, if you view it, you can actually view it as, this is a constant bias, therefore you actually see RO1. So what happened is that your circuit, you can simplify it as this. M2, VB2. The bottom circuit will simply be, you only see the effect of a resistance. So I'm seeing RO1, right? So this is equivalent to this. So I'm looking in from here for output resistance. Go back and look for common gate at its output terminal. So your output resistance, and go back to check the equation, is 1 plus GM RO. This will be transistor number 2. And amplify RS, whatever you look at underneath. So remember, if this is an RS, this is RS. But now it's RO1 plus RO2. Go back to use the equation of common gate output resistance when you have source resistance at the bottom. So this is self-source resistance. OK? So this will be approximated by, assuming that you ignore the 1, you ignore this, then it should be GM2 RO1 let's say in most cases, because I'm using a single branch transistor and also single branch, and typically if your size is the same, so you can assume that if, this is not necessarily always true, but if GM1 equals to GM2, RO1 equals to RO2, use 2 identical transistors, what happens is that you will actually get something similar to GM RO squared. OK? So you actually flatten it out by, or if I'm rewriting this, by a factor of GMRO. This is how much it flattened down. And it will flatten down by a ratio of GMRO. Originally, if it was 1 transistor, it's a 1 RO times by a factor of GMRO. So it's a very effective way of increasing output resistance when you do the stacking.